Scientists and astronomers have always been curious about the peculiarities in our solar system, and at the very top of their list of curiosity is dark matter. Although several phenomena have been unraveled by different scientists, the mystery that is dark matter still remains largely unsolved. In a bid to satisfy their curiosity, a team of scientists while researching about dark matter have recently discovered a portal leading to the fifth dimension, and this discovery is set to change how we view the universe forever. How did the scientists find the portal, and how would this discovery affect our world? Join us as we explore how scientists just announced that they found a portal to the fifth dimension. Dark matter has long since been an enigma to scientists and astronomers. Although it takes up most of our universe, scientists have yet to fully unravel its mystery. With the discovery of the fifth dimension, scientists believe that this dimension might explain the 75% of dark matter that has not been observed yet. Even though we don't know much about it, most of our ideas about the physical universe relies on the concept of dark matter. Scientists are rooted in this idea simply because dark matter takes up most of our universe, and it is regarded as a pinch hitter that helps scientists understand how gravity works. They believe several features would dissolve or fall apart entirely without an X factor of dark matter. Even at that, dark matter does not disrupt the particles we see and feel. This means it must also have other special properties, hence why more research on dark matter was needed. The quest to get more information about dark matter and its properties led a group of physicists from Johannes Gutenberg University in Mainz, Germany, to conduct a study. This study proposed a theory about some unknown particles moving around in a hidden fifth dimension. In their study, they proposed that the gravity of this particle could manifest itself in our four-dimensional universe as the extra gravity we currently attribute to dark matter. Published in the European physical journal C, the study suggests further that the particle can give a solid explanation for dark matter. This phenomenon has never been studied directly but is believed to comprise most of the universe's total mass. In the study, the researchers say particles could travel across the whole universe, including the fifth dimension that has just been discovered. For decades, scientists have questioned the four dimensions of our universe. These dimensions are known as the three of space, up and down, left and right, with back and forth, and one of time. From the extensive research carried out by scientists, the results have produced 5D equations, which suggest that the implications an extra dimension would have on the universe and even reality itself. The authors of this study, Adrian Carmona, Javier Castellano Ruiz, and Matthias Neubert, mentioned that the fifth dimension's discovery was not what they planned. Their initial intention for this study was to explain the likely origins of fermion particles in theories with a warped extra dimension. But as the scientists researched 5D equations and how they relate to fermion particle masses, the scientists came up with a new sketched-out scalar. The scalar is a physical quantity that is mainly described by its magnitude. This newly sketched-out scalar was associated with the fermion particles, and they claim it is very similar to the Higgs boson particle and the Higgs field. They found out the new scalar field had a unique and interesting behavior along the extra dimension. Having made this discovery, they said in a statement, "We believe the existence of these heavy particles would join the visible matter that we know and that we have studied in detail the constituents of dark matter. We believe this based on the assumption that dark matter is composed of fundamental fermions which live in the extra dimension." In their study, the authors described the heavy particle as a possible new messenger to the dark sector. Their theory explains even the abundance of dark matter in the cosmos as observed by astrophysical experiments. It allows more exciting methods to find the constituents of dark matter. It would be done via a detour by passing through the extra dimension to get clues about the dimension's physics at a very early stage in the history of our universe when dark matter was produced. The study's lead researcher, Matthias Neubert, made a statement regarding their discovery. He mentioned that after years of possible confirmations of the team's theoretical predictions, they are now confident about the mechanism discovered by him and his team. He continued further, "We are confident because the mechanism discovered would make dark matter accessible to forthcoming experiments due to properties of the new interaction between ordinary matter and dark matter. It would be mediated by our proposed particle and can be calculated accurately within our theory. Therefore, we hope the new particle may be discovered first through its interactions with the dark sector." Although creating a hypothesis about the particle and its mass is just the beginning, or simply put, the easy aspect, now these scientists would have to look for it. An example is the Nobel Prize-winning discovery of the Higgs boson. The Higgs boson was spotted by the Large Hadron Collider, which is the world's largest, most powerful particle accelerator. The Higgs boson's discovery was not achieved until 2012, and its hypothesis was initially proposed in 1964. Unfortunately, the Large Hadron Collider would not be large or powerful enough to detect this new particle, as it's too heavy for current colliders. Regardless, the scientists that proposed this study are keeping their fingers crossed, hoping that the particle could be detected more indirectly. They believe this new particle could play a very important role in the cosmological history of our universe. Also, they believe it might produce gravitational waves that can be detected with gravitational wave detectors soon. And speaking about dark matter, observations from the Hubble Space Telescope have suggested a missing ingredient in dark matter theories. During a recent observation of the 11 galaxy clusters, astronomers noticed that cluster galaxies give off 10 times more gravitational lensing effects than expected from cosmological simulations. This is why scientists reviewed this phenomenon and believe that dark matter halos are bigger and denser than predicted to be in the standard cosmological model. In 1933, Fritz Zwicky, a Swiss astronomer at the California Institute of Technology, was observing the Coma galaxy cluster when he noticed something absurd. He saw that the single galaxies were moving too fast for the cluster to still remain whole according to the measure of visible mass. Only a specific amount of invisible matter could shed light on the powerful gravitational force keeping the galaxies bound. After that incident, scientists reviewed the phenomenon and named the matter dark due to its inability to emit or absorb any form of light. The only way to notice or reveal its presence was through gravitational interaction with ordinary matter. Since then, more research has been done about this so-called dark matter. The observations from various studies propose that this unusual phenomenon is a huge part of the universe's matter and holds approximately 75% of the universe's matter. In the standard cosmological model, it is referred to as cold dark matter. Cold dark matter is believed to consist of massive interacting particles, but they're weak and their physical nature remains a mystery. In this perspective of CDM, dark matter halos that are gravitationally bound would form a hierarchical structure. These dark matter halos would begin with the most massive systems forming through mergers of smaller ones. As the dark matter halos form together in this hierarchical structure, large dark matter halos would contain smaller substructures in the form of embedded subhalos. In this case, galaxy clusters are similar. They also have large dark matter halos containing hundreds of galaxies gathered in subhalos. The evolution of these galaxy clusters with the interplay amongst luminous and dark matter is observed carefully and studied theoretically using cosmological simulations. These observations and comparisons permit scientists to test the standard cosmological model. Galaxy clusters are the most important structures bound together in our universe. Their total mass can surpass a quadrillion solar masses. When you examine it through Einstein's theory of general relativity, their enormous mass diverts the light of distant galaxies, sometimes deforming their shapes and splitting them into multiple images. The process of observing this phenomenon is known as gravitational lensing. Gravitational lensing allows scientists to find the spatial distribution of both ordinary and dark matter in the cluster cores, where the density's mass is very high. The principle for gravitational lensing is not a hard process. All scientists have to do is reverse engineer the observed image distortions to deduce the lens's mass distributions. This technique was used with tens of imaged galaxies lensed by 11 massive galaxy clusters recently observed with the Hubble Space Telescope. The observation was done in the framework of two programs, Cluster Lensing and Supernova Survey with Hubble and Hubble Frontier Fields. To improve their ability to compel the total distribution on the smallest scales, astronomers use the multi-unit spectroscopic explorer mounted at the Very Large Telescope in Chile. With the telescope, they measured the star's velocity dissipation in several galaxies across 3 clusters. These clusters are MAX J12060847, MAX J04161240 and Able S1063. Stars operate on the effects of gravity, so their momentums are a deputy of the subhalo masses. The team of scientists was able to get high-resolution mass maps of each galaxy cluster by combining gravitational lensing with the galaxy kinematics measurements from MUSE, a powerful wide field, and an optical integral field spectrograph. These maps also showed that these cluster galaxies are hosted by dense, huge dark matter subhalos. The images of distant sources lensed by foreground galaxy clusters have angular separations of several tens of arcseconds. As a result, subhalos within each cluster acted as smaller-scale gravitational lenses embedded within the large lenses. Supposing these subhalos are big enough and have sufficient density, they could produce additional local strong lensing events on smaller scales with smaller separations of less than a few arcseconds. Results from the scientists' lensing mass reconstructions brought about these events called galaxy-galaxy strong lensing (GGSL) events in each of the observed clusters. After that was achieved, scientists compared the observed cluster mass distributions to 25 simulated galaxy clusters, which evolved in the standard cosmological model. This comparison revealed that cosmological simulations do not depict the same dark matter concentration level on the smallest scales. This is why they produce more than 10 times galaxy-galaxy strong lensing events than we observe. The outcome of these results suggests that there are some characteristics of the universe that we do not understand yet. Therefore, the number of observed GGSL events is inconsistent with theoretical predictions about the standard cosmological model. It might also be an issue with the simulation methods, or we could have made the wrong assumptions about dark matter properties. However, more observations will be done with equipment such as the European Space Agency's telescope and NASA's planned Euclid. The Nancy Grace Roman Space Telescope could also be used to confirm the problem and help clarify issues by increasing the cluster samples that can be examined. This would help scientists and astronomers to progress in stress testing dark matter models.